Okay, so we just learned how to solve systems of equations where if they were distinct lines and unless they were parallel, always intersect at one point, which gives us one xy point solution for the system of equations, the two variables, whatever they might represent in a word problem or otherwise. How do we go about solving systems of linear inequalities? Well, in this case, it's going to be different. There is not just one point of intersection or one point solution. You're going to have an intersection of entire areas of solution sets. So you're essentially going to have infinitely many points within a region of intersection that's going to be your solution set for the inequality system. Let's take a look at that in this case. Suppose I had two slope-intercept y equals or greater than mx plus b type format inequalities. How would I go about solving it? Well, the first step is I'm going to look at my first equation, or I should say my first inequality, but I'm going to treat it like equation. Y equals 4x minus 3. I know how to graph that. That's going to be a y-intercept of negative 3. It's going to have a slope of 4, so I'm going to go over 1 in x and up 4 in y. Over 1, up 4, and I can graph that line. Now I'm going to be careful. It's actually not equals, it's greater than, which means the line itself or the points on the line are not included in my solution set. If that's the case, I'm going to use a dashed line for my graph to see the solutions here. Remember, the points on the line are not part of, but all the y points greater than that line, which is essentially everything above that line, are solutions to my inequality. Okay, see how that works for that inequality. Let's try the second inequality. Y is greater than or equal to negative 2x plus 3. So again, I'm going to graph the line as though it were an equation, because I know how to do that and visualize it fairly easily. Y equals minus 2x plus 3. That will have an intercept, a y-intercept of plus 3, and it's going to have a negative slope. So if I go over 1 in x, I'm going to go down 2 in y, and vice versa, and I can keep plotting those points out. Now in this case, notice greater than or equal to. The equal to indicates that points on the line are part of the solution set, which means I fill in a complete shaded line, not a dotted or dashed line. This is to indicate that the points on the line are also part of my solution set. Now, greater than, every y greater than or equal to that line is part of my solution set. Well, guess what? That's everything above the line. Y's are greater than that. So what is my final solution set? How would I look at this? Well, my final solution set is going to be the intersection of those two. It's going to be everything above the one line and everything above the other line, the intersection of the purple and green regions, which is effectively this region in here. That will be the area of my solution set. So you might ask, well, I see it intersects at 1, 1. That's pretty obvious from the graph. Is 1, 1 part of my solution set? The answer is no, it's not. It's only a solution to one of the inequalities, the greater than inequality, the dashed line. It's not part of the solution set. So it's not a solution to the system. So be careful of that. That intersection point in this case is not part of the solution set. If they were both greater than or equal to's, it would be. We can run a similar exercise on standard form inequalities as well. Note in this case we have two inequalities in standard form. I might begin by graphing the equations. X plus y equals 2. Well, how would I graph that? I'm going to plug in x equals 0. I know y equals 2 and x equals 0. And I'll plug in y equals 0 to get the x-intercept. X will equal 2 when y equals 0. I'll connect those points and I get the line for x plus y equals 2. But again, I want x plus y is greater than 2. I'm not going to convert it to y equals mx plus b format, but I can see y is going to be plus y is going to be greater than the rest of the expression. So that's greater than. That's going to be a dashed line. My solution does not include the dashed line, but every y greater than that is going to be in my solution set. So all y values above the dashed line. Okay, well, let's try that for the second inequality. 2x minus y, and let's suppose for a moment it equals 1, so I can graph that. Again, I might plug in 0 for x to get y. Y equals -1 in that case. So when x equals 0, y equals -1. And I can plug in 0 for y to get my x-intercept. So 2x equals 1. X will equal 1/2 when y equals 0. And I can begin to then graph the rest of that line. But again, I know it's an inequality, and it's a greater than symbol here. So it's going to be a dashed line, just like the other one, not part of the solution set. Sorry, not the best dashed line, but did the best I could. And in this case, I know minus y is greater than. So really, if I added y to both sides, I would have y is less than. So the region I'm looking for is all y values below the pink dashed line. And I know my solution region is going to be, therefore, the intersection of the two. It's going to be below the pink dashed line and above the green dashed line, which is effectively this region right in here that I'm shading in light blue. Again, the intersection point and all points on the line will not be in this solution set. Okay? And if I wanted to find a particular point that's in the solution set, well, hopefully it's obvious graphically, but your more accurate way is to plug that point back in the two inequalities and check if that works. Systems of linear inequalities can also present as word problems. So, for example, the school needs to buy hardcover books and softcover books. Softcover books cost $10 per book, and hardcover volumes cost $30 per book. If the school buys no more than 20 books and can spend at most $500, which inequality represents the situation? So how do we find and set up the right inequality that reflects this word problem? Well, we again know we have the situation where we have price times the number of hardcover plus price times the number of softcover equals the total expenditure. So I'm going to say the price of the hardcover, which we're told is $30, times the number of hardcover books, let's define that variable as H, plus the price of the softcover, $10, times the number of softcover books, we don't know that, so let's call that variable S, must be at most 500. So what does that mean? That means it could be 500 equal to, but it can't be anything more. It has to be less than or equal to. So the correct inequality for the price and amount is 30H plus 10S is less than or equal to 500. We also have the equation for the total amount of books. We're told the school buys no more than 20 books. So the number of hardcover books they buy is H, plus the number of softcover books they buy is S. That's no more than 20. Can that be 20? Yes, it can be. Can it be more than 20? No, but it could be less. So again, this is going to be another less than or equal condition. It's going to be less than or equal to 20. Slightly different wording, but again, you have to translate the wording into the correct inequality. Less than, greater than, less than or equal to, or greater than and equal to for the appropriate scenario and word problem. This is the answer that represents the system in the word problem. And that brings us to the end of Class 2 of Heart of Algebra. We've now completed all our linear function work and overview for Heart of Algebra. The next step is going to be nonlinear functions, advanced mathematics, quadratics, exponentials, etc. Are you ready?